back to the example. Suppose the 8 trials of the above experiment. So one more time, 8 trials. We have 4 different treatment combinations, 1, 2, 3, and 4, and we run each of those twice for 2 replicates. So suppose these 8 trials are run in a completely randomized manner, and the results from the trials are shown here in the graph. This is what we had in the table. This 73, 48, 60, and 83. Those are minutes for mowing the lawn. Now the results, then we have this in this graph, and we can see that the corners of the graph represent the treatment combinations. And here it's very easy to see which is the best treatment combination for mowing your lawn quickly. Treatment combination 2 gives us the best result, requiring only 48 minutes, the least amount of time to cut a yard of a given size. Now, the problem is that the results normally do not come out this clearly from many real experiments. There may be differences in the results from the replicates of the same treatment combinations. The results from various treatment combinations may not be far apart enough to give a clear-cut choice. The results from the trials of treatment combinations may even overlap. So when the differences among the results from the treatment combinations are not far apart, showing obvious difference due to factors, we would want to know whether the differences in the results are indeed true differences because of the factors or just due to experimental variability. So in such a case, we would then have to calculate the effect of the individual factors and the effect of the interaction among the factors using a statistical technique to determine if these effects are significant. So next, we will calculate the effects of factors A and B and the interaction effect of A and B for this example. First, we will introduce a simple nomenclature. So symbol 1 indicates the treatment in which both factors are at a low level. The symbol little a is the treatment when factor A is at the high level and factor B is at the low level. Factor little b is the treatment when factor B is at the high level and factor A is at the low level. And factor AB, little ab, is the treatment combination when both factors are at a high level. And just a reminder, we are always using the averages from the treatment combinations when we do our analysis. So here we have all the data together. We have this rearranged from our experiment where we have treatment combination 1, 2, 3, and 4. We've also added 1A, B, and AB, as we just discussed. We have this rearranged in a table where here you see the different treatment combination codes, and here you see again the different factors. Treatment combination 1 when they're both low, treatment combination AB when they're both high, and this time we have a new column with the heading interaction. So these are called now design columns here with the original factors and a calculation column. Now these codes then, we're going to use them to represent the average response from the different treatment combinations and the formulas that are given next for calculating the effects. So let's review what those are. The effect of a factor refers how changing the settings of a factor changes the response. And the main effect of a factor is calculated by subtracting the average response at the 2 treatment combinations where the factor is at the lower level from the average response at the 2 treatment combinations where the factor is at the higher level. And if we use our nomenclature, we can then write out the equations for A and B as follows. So now if I want to do this calculation, here I have my different treatment combination codes. Here I have my averages that I've measured, average from the 2 replicates. A is equal to -1 plus little a minus b plus ab. So for the main effect of A, we can write this then as negative 73 plus 48 minus 60 plus 83 divided by 2. So you take the average value according to the treatment combination code and perform the summation here that we have. And we get for that, we get the value of negative 2 over 2, which is equal to negative 1. So negative 1 is the main effect of factor A. And likewise for B, time we have negative 73, this time minus 48 plus 60 plus 83 divided by 2. We get there 22 over 2, we get 11. And that is the main effect then of factor B. Does everybody see that? Okay, so what do these mean? We have the main effect of A is 1. The main effect of B is 11. So remember, factor A was the blade angle. We varied that between two different levels. And factor B was the deck height for the lawnmower. If the blade angle factor A is changed from its lower level of 12 degrees to its higher level of 60 degrees, then the mowing time is decreased by 1 minute. That's the negative 1. If the deck height, which is factor B, is changed from 5 inches to 7 inches, then the mowing time increases by 11 minutes. That was the main effect of B. So, we now have calculated the main effects. We now need to consider one more thing, and that is the interaction between the effects. Now, interaction between two factors exists if the effect of the two factors acting together is much more or much less than the sum of the effects caused by the individual factors acting alone. And it's necessary to detect the existence of interaction between factors because, as we'll say later, when significant interaction exists, the main effects then are not considered useful. The interaction effect between two factors also has a practical meaning and can help in understanding how the factors work together. So, the interaction effect between factors A and B in the two-factor experiment is calculated as follows. We take the averages of the responses from the treatment combinations where both factors are high and both factors are low. So take the average of these two values, and then we take the average of the responses from the treatment combinations where one factor is high and one factor is low. And we subtract these, and we get the following formula. So, one more time, we have this time 73 minus 48 minus 60 plus 83 over 2. This gives us 48 over 2, or an interaction effect of 24. And what this means is that increasing both the blade angle and the deck height together increases the mowing time much more than the sum of the effects from increasing them individually. There is considerable interaction between factor A and B. Now, all those little equations, we have a shortcut for calculating the effects using our table. First, what we need to do is to calculate the so-called contrast of each factor. And what this means, the contrast is the product of the column treatment combination codes and the column of signs underneath a factor. So, for factor A, we have minus, plus, minus, plus, minus, plus. For factor B, we have minus, minus, plus, plus. So the contrast of factor A is going to be then minus treatment combination code 1 plus little a minus little b plus ab. So we get minus 73 plus 48 minus 60 and plus 83, which gives us then the value of negative 2. And likewise for factor B, we would say minus 70, I can write this in here, this would be minus 73 plus 48 minus 60 plus 83 gives us 2, minus 73 minus 48 plus 60 plus 83 gives us 22. These are called the contrast of the factor. Now, the effect of the factor then is just simply the contrast of the factor divided by 2 to the power of k minus 1. And in this case, we have k equal 2. There are two different factors. So 2 to the power of 2 minus 1 is 2 to the power of 1 equals 2. We divide these by 2, and we get the values of negative 1 and 11, which is what we had on the previous page. So it's the same calculation. It's just if you look at your table, you can then calculate the effects much more simply. Okay. Now, so we now are interested in the significance of our results. What we have is our lawnmower experiment. We have different treatment combinations that we've tried, 4 different treatment combinations. We've done 2 replicates, and we have a response. We have used that data to calculate the effects, and we calculated the effect of factor A to be minus 1, the factor B to be 11. And so we realized that if you varied your factor A by a certain amount, you would get a decrease in your mowing time. Factor B, we had an increase in our mowing time. But are these results significant? And the analysis of variance, or ANOVA method, is normally used to answer this question. And we'll look at that in the next lecture. But we can already look graphically at the significance of the interaction effect.